beautiful.
I think it has to be flashed out.
So you want to test it or no? Okay.
Sorry, we'll see if. I mean, like, if this doesn't have to be. Well, trouble to find something else. Yeah. I'll try. What do you mean? Nature clones? Oh, I thought you were going to say nature. Yeah, actually, yeah. I think checking for it.
Yeah. What should I do? Just check whether it is.
Just check.
Okay.
Especially if you have video or something like that.
Yeah, I think it is working. Thank you. Can I leave the charger here or like should I take it?
You can do it. Well, I'm not a chair, but
Oh, okay.
I think it's fine. Just put it here. Just yeah.
Once you have a language of communication, that's actually like I feel that's right. But he has a pretty cool.
This is the sign for whether you agree on uploading, recording and uploading your talk.
This is what.
So I give this one is agree, this one is do not agree.
Which one
uploading.
Which one you agree?
Oh yeah, for this one. And then name.
Oh shit.
And your paper ID.
Which I don't know.
It's fine now, I just write it up.
Thank you.
So we're gonna start off at 3:5 in 3 minutes.
Okay.
All right, everyone. Welcome back. Now, in this afternoon, we have a great paper session, Wave Optics for Imaging and Display. I'm the session chair, Seung-Han from Postech. And today we have 4 papers in this session. And the first 2 we're going to be on-site. We have 2 presenters. And then the third presentation, we're going to be, unfortunately, online. So we'll try to connect to the Zoom. And the last one, we're going to be, again, like in-person presentation, fortunately. So, yeah, without further ado, I think our great presenter, Evan, can start.
Okay, great. Thank you so much. Hi, my name is Evan from the University of Hong Kong. So I'm so glad to be back physically for ICCP after a few years. And unfortunately, the first and the second author of this paper, they both couldn't get here because of a visa issue, although they have submitted their visa for over 3 months, but still pending. So yeah, and today I'm going to present this word about off-aperture encoding under this kind of a. Let's see. This is the joint work between Hong Kong U and KAUST with Wolfgang. So I guess like the topic of deep optics, or sometimes we call it lens optics for domain-specific imaging, has been transforming all the design in this community. And I'm sure most of the audience are familiar with this topic. So long story and short sentences would be like, traditionally, the camera optics is designed separately from the image post-processing algorithms. And recently, empowered by AI advances, especially the differentiable end-to-end optimization pipeline, we can try to co-design the camera optics and the computational algorithms. So we try to treat the optics like as the encoders and the computational algorithms as decoders so that we can extract the domain-specific information. Okay, so the specific focus of this specific work is on a very common yet challenging problem. So we try to achieve the wide field of view with a highly compact imager. So now if we try to achieve a wide field with just a small thin lens, we immediately try to run into a major hurdle like this. A simple thin lens, but with severe aberrations. So light rays coming from wide angles, they get burned in all sorts of wrong ways. And traditionally in the optics, we try to stack multiple elements so that we can try to mitigate aberrations, but ending up with a bulky system. And this is where the co-design comes into, aiming to find the optimal balance where the well-established concept of Off-Aperture systems in computational imaging community can actually stand out, right? However, one thing to know, the form factor of the imager is not only affected by the thickness or the weight of the optics itself, but also the considerable air gap in between the lens and the sensor plane. So sometimes we call it the back focal distance. So nonetheless, given this space, we try to see if we can explore the slightly different encoding in optics. So traditionally, we have the Off-Aperture systems. So let's say we have a diffractive optical element, DOE, and it's placed right at the aperture plane, which is like the lens. And the issue here is that all incoming light, regardless its angles, passes through the same small region of that DOE. And this gives us like only a global control over the wavefront, which is good in many cases. But let's just play a very simple idea. Intuitively, if we move the DOE towards the sensor because there's an air gap, the light from different angles has its different regions, right, on the DOE. And this, to some extent, enables the local wavefront control. Then we can try to design the DOE to have more precise modulations that each bundle of light for different angles needs. And this somewhat breaks the trade-off between the performance of on-axis and off-axis performance. So if we look at the point spread functions like here, you see that around the optimal positions, both the central field of view and outer field of view actually maintain a high local contrast, which we believe is actually essential for subsequent CNN-based reconstruction algorithm. So you can also check from the metrics that the performance boost of around 5 dB in PSNR. So when we try to place the DOE in between 0.2 to 0.3 of the air gap. Okay, so now the key is to enable the optimization in the deep optics for this kind of challenging wide angle sceneries. So we need an off-axis simulation tool for light propagation that is both precise and fast. Because now the DOE may become larger than the aperture because we have put it into between the sensor and the lens. So compared with the previous solutions like all of these, we have this called sampling angular spectrum master algorithm, try to offer several advantages. So it's kind of fast, more accurate, and crucially, it's differentiable. So we build this on top of an angular spectrum, but provides a mathematical formulation to specify the minimum sampling requirement for the optical field. So here's some details. So we try to propagate the light at an angle, and usually you have the linear term, right, in the phase, so that we can cause a translation in the frequency domain. And if you sample this in the usual way, you get a lot of aliasing. So what people do is try to zero pad, right? This ending up with huge computational memory burden. So over this sampling angular spectrum, try to calculate the shift and the minimum sampling window to minimize the sampling requirement. And this results in around 30x faster simulations at the ultra large angles, like 45 degrees. And details could be found in the paper. So let's have an overview about the state of art. So compared with previous cold aperture systems, we employ this kind of shift variant point spread function modeling and the end-to-end optimization. So we can achieve a considerable wide field of view for both RGB images and RGBD imaging tasks. Okay, so as usual, we need a forward imaging model and the algorithm decoding part. So in the optics, we developed two systems to prove the concept. So the first design features a simple lens and an off-aperture DOE targeting color imaging at a single depth but a large angle. The second design uses an optimized Cook triplet simulated with a differentiable ray tracing and our this sampling angular spectrum master propagation. The decoding side, we have a lightweight neural network containing a shared feature encoder which learns the common representation from the optically encoded images. And then from this shared feature, the network can actually break into two decoding heads, each is trained to perform a separate vision task. And because our images are large, the DOE is large, we try to compute the losses on multi-scale output. So we developed two camera prototypes for 45-degree RGB imaging and around 30-degree RGBD imaging. So we have used the off-the-shelf optics as well as diamond turning freeform lens and also the photolithography fabricated DOE. So here are simulation results. The off-aperture reconstructions are sharper, as you can tell, than the on-aperture, both for the center and the outer field of views. So in addition to the thin lens we purchased, just one simple lens on the market, we also fabricated the DOE, and we also 3D printed the mount for easy calibration. So second example, we have compute with the near aperture case. This is because we actually cannot enable the simulation of DOE in between refractive lenses yet. But still, we observe quite good results in simulation, including the recover patches, as well as the much better depth reconstruction in several regions. So here we have the quantitative results showing around a 20% reduction on the depth error metric. So in the design triplet, we CNC diamond turn an acid flicker lens and purchased two spherical lenses from the market, and also there's a lithography fabricated DOE. Okay, now let's see the real experiments. So here are the real experiments of both indoor and outdoor environments. We can see the sharp detail between recovery in all field of view. So that's the reconstruction. Let me talk them back first. So this is the capture result and reconstruction. So we also have a video captured and try to reconstruct to prove its robustness for the real world scene. And now the second application, we reconstruct both the image and the depth maps from the coded measurements, given the information from the special variant point spread function cubes. So like this. Okay, so what will be the signature backslides? The first backslide for wide field of view imaging, people always think about pinhole, right? Because ideally there should be no aberration. So a pinhole can capture image with almost no aberration, but it suffers from a very low light throughput like this. It's not totally black, but yeah. So we apply the state-of-the-art low light image processing algorithm to brighten the images so that we have results like this. And then we have the iPhone 15 capture reference image over there. Then this is our thin lens off-aperture encoding only one single lens. Okay, the second baseline, we'll think about what if we don't need a DOE, right? So this is a comparison with a 9-code aperture camera paired with a reconstruction network. So you can see that our reconstruction also sharper and all angles, like these. Okay, to summarize, we have co-designed an imaging system that leverages the off-aperture DOEs for spatial and angular encoding, so that this can enable a local wavelength control beneficial, especially for wide field of view imaging. And you can scan the QR code for more information about the paper. And still, we are suffering from some artifacts, also the light efficiency loss. Yeah, thank you for your attention. But before ending my presentation, I still have time. So I'd like to broadcast a little bit about this year's SIGGRAPH Asia 2025 will be in Hong Kong in December. Welcome. Even though it's December, it's still pretty warm in Hong Kong. And come to Hong Kong not just for SIGGRAPH Asia, but also for this amazing view. So Hong Kong is a nice city, and this is actually the view you can capture from the top of Hong Kong U. Hong Kong U is located right here. But in addition to this kind of like dense, fancy high-rises in Hong Kong, we are also full of like these things. So 70% of the landscape in Hong Kong is actually natural reserve. We have a lot of islands. So we have like the Dragon's Back, which is like voted by Lonely Planet as the Asia's best urban hike. So welcome to Hong Kong, and thank you for your attention.
Yeah, thank you for the nice presentation and advertisement on the SIGGRAPH Asia as well. And is there any question from audience? We have. If not, I first have a question on the. Like, it is interesting that this you consider spatially varying wavefront correction using this off the aperture plane DOE. Like, have you tried to analyze this learned the DOE pattern at different distances from this aperture plane?
Yes, that's a very good question. So in the paper and also the supplementary, we actually implemented 2 different experiments, including a heuristic design of different DOE positions, but also the end-to-end joint inland DOE positions. And it's actually very interesting, like the result of both like agree with each other very well. And yeah, we have provided all the details in the paper.
All right. Any other question? No. Then I have another question. Like here, instead of having only one DOE at a fixed location, like could we also think about having multiple DOEs in a lens? And then, do you have any like guess on the degree of freedom that we can gain from that, and also some of the potential challenges?
Of course, I mean, I guess not just us, also different groups are exploring the state of like multiple elements, including but not limited to reflective optics, diffractive optics, and maybe more, including like meta surfaces. I guess right now we really need a very accurate and efficient simulation tool to model over the different kinds of light propagation in between different kinds of elements. So I think, yeah, it's actually ongoing future work.
All right, let's thank Evan again for the nice presentation.
Thank you.
Yeah, our next speaker is Dorian. He's going to talk about something cool about this holographic display.
Okay, hello. Thank you for attending my talk today on leveraging high-speed holographic displays for dynamic content. So what does this actually entail? Well, let's start with the basics. So holographic displays fundamentally show desired content by inverting the propagation of laser light. And typically this process looks something like solving this optimization problem I've written up here on the screen, where you're trying to find the SLM, the spatial light modulator pattern, that best reproduces our desired target content after propagation. And just to give a bit of bigger picture here, these holographic displays have seen a lot of attention in the context of AR/VR, and I'll argue that this is primarily due to two reasons. First and foremost, these systems are capable of naturally displaying realistic 3D content, and they can also perform glasses-free vision correction, and these are two big pain points in current AR/VR systems. But secondly, you can also do all of this in a very compact form factor, and this makes these systems a really attractive choice for future AR/VR displays. But unfortunately, there's no free lunch, and these things also have challenges associated with them. And perhaps the biggest one that I'll talk about today is what we call speckle. And to illustrate what the speckle is, let's just say I wanted to show this 3D content on my holographic display. And what I would actually see is something closer to this. And these noise-like artifacts that you can see on the screen here, at least are what we call speckle in the context of these holographic displays. And I think there's a couple of explanations for why this happens, but perhaps my favorite is that fundamentally our holographic displays use coherent laser light to show their desired content, but what we actually want to show is incoherent content that we as human beings are used to seeing. We're not used to seeing laser light. And this kind of mismatch is basically where the speckle comes from. So of course, this is a really visually distracting artifact. So people propose like so many different solutions in the literature, but perhaps the most enduring over time has been what we call time multiplexing. And if you're not really familiar with this concept, well, long story short, we as human beings have this visual property of persistence. And at least in the context of displays, what this means is that if we have a really fast SLM, we could potentially display a lot of frames very quickly, and our brain will actually go and average these frames together. And this averaging basically ends up being a really nice tool for removing speckle, in that we could potentially take our frame and show it many different times with different speckle patterns. And in expectation, that speckle kind of will average out. And there's a couple of ways you can actually do this. I think perhaps the simplest is what we colloquially call independent time multiplexing, where basically I independently show every individual high-speed frame. And mathematically, you kind of think of it as basically going and solving that optimization problem I had from earlier independently for every single high-speed frame I want to show. But if you actually look at this output image and you like zoom in a little bit, you'll notice a couple problems here. First, you actually get this pretty bad loss in contrast. And I think this is fundamentally because you basically have a biased system. It doesn't really actually average out to the correct intensity and expectation. But secondly, our SLMs aren't really fast enough. And as a result, right now, at least on modern SLMs, we get pretty bad conversions, just averaging the speckle out over time. So how do we actually fix this problem? Well, I think today's solution is to try to do something a little bit smarter and maybe try to actually correlate our speckle between these different frames. And the most common way this happens is that if we have some frames, we can optimize the output of this model. And colloquially, again, we call this joint time multiplexing because basically we are jointly optimizing all of those SLM frames together to reproduce the target. And this actually works pretty well. You zoom in here and yeah, we get much better contrast, much more reduced speckle. And today, these fast LMs are pretty common, and as a result, they are basically the default, shall I say, on state-of-the-art holographic displays. Unfortunately, these types of systems we observe in our work will actually struggle with dynamic content. So what do I mean by this? Well, let's just say I actually want to show some continuous real-world scene, like I have here on the screen, right? Like a sign that is like moving to the right relative to the viewer. And if I were to show this on a traditional time multiplex display system, what I would do is I would go and sample a couple of discrete frames from the sequence and then time multiplex them. And this process, the sampling process, is basically where the problems start to arise. And to kind of illustrate this, we as human beings, we often actually move our eyes when we're looking at dynamic content. And there's a couple different phenomena, as I've kind of alluded to here, where this actually happens. Perhaps one really, I guess long story short, without getting too bogged down in the details here, is that basically our eyes are rotating to make sure that moving objects stay stationary on our eyes. So for example, this sign, our eyes will rotate to basically keep it on our fovea. And basically this process basically makes sure that after persistence of vision, we actually still see a sharp image of this moving object. Unfortunately, in these time multiplex displays, we're kind of sampling discrete frames while our eyes like move continuously. Like our eyes don't like just jump around. Our eyes are actually still continuously following the sign. And because of this mismatch, after persistence of vision, you actually get a lot of blur. And it turns out that this blur is actually really well known in the context of AR/VR systems. It's called sample and hold blur. And it's really well known to cause nausea and visual discomfort. So, of course, engineers in that space have spent a whole lot of time trying to fix this problem. And perhaps the current de facto solution here is you use a low persistence display. And for all the imaging folk here, you kind of think of it as the analog to a low exposure, to a short exposure to deal with motion blur. It's exactly the same principle, where basically you flash on that content per discrete frame, and after persistence of vision, you actually get this nice sharp image. Unfortunately, this doesn't work for time multiplex systems in that if I'm flashing this on, I'm just not really doing time multiplexing. So I get a specular output afterwards. Now, this isn't the only perceptual artifact that happens. Now let's just say my eye actually isn't tracking this object. And in the real world, if this was happening, my eye would actually see this nice motion blurred version of this sign. But in my time multiplex world, what happens is I've sampled these discrete locations, so I actually get these like really annoying sharp artifacts in my perceived images. So it turns out that these are called stroboscopic effects in the context of AR/VR, and again, they are known to cause nausea and visual discomfort. Unlike that sample and hold blur case, there isn't really like a good solution so far, at least in the current AR/VR literature. The traditional approach, quote unquote, is you basically go and artificially add blur to your output content, but it turns out that this is actually pretty visually uncomfortable because our eyes are not really used to seeing artificial blur. So, how do we actually avoid these motion artifacts? And I think perhaps the key insight in our work is that if we had a perfect infinite frame rate display, we would actually have no problems because we could go and perfectly replicate the real world. But when we think about our time multiplex systems, what we actually have is a fast SLM. And this fast SLM you can actually think of as a high frame rate but corrupted display. So if we were to actually use this SLM as a high frame rate display, what would happen is that you actually don't get any of those perceptual artifacts. I really should have zoomed in here. You don't get any of these perceptual artifacts, but if you actually zoom in a little bit closer, what you'll notice is that we actually have the same bias and convergence problems from before, where that black level is pretty bad. So how do we actually fix this problem? At least in our work, we basically apply the same trick that we applied before. Basically, we build a model for how we actually perceive these high-speed videos. So here we actually incorporate eye motion into part of the pipeline, and we optimize the output of our model for a high-speed video. And we call this motion-aware high-speed display. And I didn't mention, but the earlier one we call independent high-speed display. So really what changed from before? Well, first and foremost, we're actually modeling eye motion, and that ends up tackling most of those sample and hold blur problems. But secondly, we're actually working directly with these high-speed videos, and that ends up solving a lot of the stroboscopic artifacts that we were talking about before. Now, before I move on, one caveat is that eye motion is actually a really tricky beast in that you need like eye trackers and stuff like that. And typically, those commercial eye trackers are not really particularly accurate. Or maybe you actually don't even have eye tracking, so you have to do some type of gaze prediction with your data. So as a result, we actually need to be able to handle maybe more probabilistic estimates of how our eyes will move. And so part of our contributions is we talk a little bit about how to handle some of these cases. And in our work, we propose a variant where we basically optimize over this distribution that we call the stochastic approach. So that's the end of the technical side. Let's look at some results. So here are some real-world scenes that I generated in Blender. And we can actually test out some of these effects that I just saw. So let's just say my eye is actually looking at this. Well, in the real world, I would see this nice sharp image of these things. But with my joint multiplexing, I get these like really blurry messes. And it's actually pretty speckly still. With this independent approach, that speckle goes away. And I don't really get any of these artifacts. But I still get pretty bad bias and convergence. I plug in this motion-aware approach, and things really clean up really nicely. But unfortunately, this requires a nice estimate of eye motion. And if I get the eye motion incorrect, you can actually see like some halos near those like darker areas. So that's not great. But with our stochastic approach, these effects usually clean up. And now let's go into that second case where my eye actually doesn't track this motion. Ground truth, I get this nice motion blur. And with that time multiplexing, I get these really artificial artifacts. This independent approach, again, cleans this up. Using that motion aware does really well, but if we get that eye motion estimate incorrect, we actually get these pretty annoying spectral artifacts. And finally, our stochastic approach really cleans this up. So before I finish, I do want to talk a little bit about the broader paradigm of our work, which is that at least in imaging and displays, we actually pretty often use these high-speed but imperfect systems without even knowing it. And I think the classic example is the rolling shutter camera. But as we've shown in our work, these time multiplex systems can also be viewed as a variant of this idea. And trying to leverage these high-speed capabilities with computational tools could be really useful. And with that, thank you for your time. I'm happy to take questions either now or at the poster session tomorrow.
Yeah, thank you for the nice talk, Dorian. Is there any question? We have time for, oh yeah, here.
You talk about fast displays.
Yeah.
What is fast?
Yeah, that's a good question. So I'm talking like 1,000 kilohertz. Sorry.
And what is the number of pixels you need?
So at least the SLM we're using, it has about, it's like 1358 by 800 pixels, and it's like it's a 1.4 kilohertz system, but I think people are trying to push this up higher and higher. Now the caveat is that these faster displays are usually quantized, and you can push them to be even faster, but you have to quantize them more. So basically it's like this high speed but imperfect trade-off that you can kind of play.
Thank you.
Yeah.
Any other question? Yeah, here.
Yeah, so you're saying that basically because you don't have super accurate eye tracking, you're using the stochastic approach. What is the trade-off in terms of amount of information you have about eye versus like how good you can make the reconstruction?
Yeah.
But like if you know the depth that you're focused on, is that useful?
Yeah, I think definitely the more information you have, the better. And I don't have it in the paper, but I can give you a theoretical proof for why you can actually get a perfect solution that works for all eye motion cases. But I'm happy to chat more about that offline. So.
Yeah, I think we have a little more time for probably one more question. There's any? If not, I actually do have a question. Yeah, so like it seems like in order to take into account these eye movements, we need to do that in real time, which is definitely feasible using the existing technology. But I think given that the eye tracked information, we need to calculate this hologram that we're going to display in real time at the fast SLM. Like how fast that could be, or is there any like challenge over there?
Right. Yeah, that's an amazing question, and we like dedicate half of our paper to that. But I think what I'll say to that is we basically have to do like the sequential processing, where like basically your data is like updating in real time, and your eye motion is like updating in real time, and all these different things. And yeah, I think definitely there's some more theoretical aspects where like in theory, like the more frames you have, the better, even if you have less computation per frame. So it's just a fun tidbit. Yeah.
All right. Thank you very much, and thanks Dorian again. Yeah, give us 1 minute for setting this up for the Zoom presentation. So the next talk is going to be the HoloZip, another holographic display paper, ultra high hologram compression via latent-of-latent coding. And the presenter is Huaizhi here.
Introduction. Yeah, I will start sharing my screen.
Yep.
Can you see my screen?
Yes, we can see the screen.
Okay, sounds great. Let me also turn on my camera. Okay, yeah, I think everything is ready.
Yep.
Okay. Hi everyone, my name is Huaizhi and today I will be presenting our paper HoloZip, High Hologram Compression via Latent-of-Latent Coding. So today's presentation will be divided into 4 parts: introduction and motivation, methods of HoloZip, experimental results, and conclusion. So holography is a technique that records and reconstructs the complete 3-dimensional information of an object, including both amplitude and phase of the light waves scattered from the object. Unlike traditional photography, which captures only intensity, holography encodes depth and spatial relationships, which enables realistic 3D imaging. By using coherent laser illumination and interference patterns recorded on a hologram, it allows observers to perceive the original object's full spatial presence from different angles, recreating a lifelike visual experience. So here is an illustration of a standard holographic pipeline. Holography uses laser light to record interference patterns, which are called holograms. And the hologram is displayed on the spatial light modulator to modulate the light, and then reproduces a realistic 3D scene at a virtual plane and can be viewed at novel view angles. So given these advantages of holography, holographic displays are gaining increasing popularity, particularly as a promising solution to augmented and virtual reality wearable displays. However, the extraction of holograms involves very complex numerical computations, requiring numerical simulation to calculate the holograms on the display that we want to use. But edge devices for AR and VR cases are constrained by the energy consumption and computing power to perform such heavy computations. So to save the energy, cloud edge collaborative computation is employed. In this scenario, cloud servers with no energy consumption constraint will take the major role of heavy computation. And the generated intermediate results from the cloud side will be transmitted to the edge device for decoding. The edge device will decode the final hologram to display from the intermediate data transmitted from the cloud side. To achieve a successful pipeline under the cloud edge collaborative principle, we hypothesize 4 points that make us ideal like such a pipeline. Cloud side extraction should preserve high quality intermediate features for transmission. And the transmission should minimize the information loss so that we can have a high quality reconstruction on the edge side. The edge side for the reconstruction and decoding should be lightweight so that we can save the energy. And we should also be able to support various content types in the same framework, like image and video under the same pipeline. So here we present HoloZip, a cloud edge collaborative framework for efficient holographic image and video compression and transmission. Here is the overview of the proposed vision transformer-based holography generation and compression framework. In this framework, we adopt vision transformer-based components for high-quality feature extraction and also for high-quality compression. The framework can be divided into encoding and decoding components, where the decoding components are deployed locally or to edge devices in a cloud collaborative computation scenario. The cloud side extracts the phase map from the input natural images or video frames, and these frames are encoded into first stage of the latent space by a vision transformer encoder to reduce the spatial side as the first stage of compression. the encoded latent map from the first stage are further compressed with the vision compression transformer to maximally reduce the data amount for transmission as a second stage compression. That's why we call our pipeline latent-of-latent coding. After being transmitted, after the second stage of the latent being transmitted to the edge side, a lightweight decoder first restores the extracted latent map from the bit flow, followed by a lightweight CNN module to upscale and restore the original spatial site to the hologram for display. In our framework, the phase extractor, denoted as IP, and the latent encoder, denoted as EP, are implemented with vision transformers. Specifically, we use swing unit and swing transformer for these two modules, respectively. In standard multi-head self-attention utilized by standard vision transformer, every image patch attends globally to all other patches. While in swing transformer, each image patch only attends to other patches in a defined local window. Therefore, we reduce the computation overhead. For example, in the illustration on the right side, for an image patch in the yellow region, swing transformer only allows the patch to attend to other patches in the same yellow region. While in standard vision transformer, in the second row of the illustration, each patch can attend to all other patches, therefore significantly increase the computation overhead. Now we come to how we do the second stage of the compression. In this stage, we incorporate vision compression transformer to support both image and video compression, and we achieve a high compression rate. On the right side is the illustration of the vision compression transformer architecture. Each frame E is first processed by an encoder denoted as EI to reduce the resolution and convert it to patches. The image patches will be used as the input for a transformer that predicts the probability distribution required for entropy encoding. For video compression, illustrated on the left panel, the statistical information from the preceding frame VI is incorporated into the prediction of the current frame VI+1 via cross-attention in the transformer, therefore enabling the usage of temporal redundancy to achieve a higher compression ratio. The right panel details the encoding-decoding pipeline when we are working on only a single frame VI. In this case, we are doing compression on the image rather than video. In this case, the frame is initially encoded by the encoder EI and transformed into patches and compressed via entropy coding, guided by the transformer estimated probability distribution. After transmission, entropy decoding reconstructs the patches with the probability distribution, which are then restored by the decoder DI to the original latent map. For the decoding, we only utilize this lightweight CNN for high decoding speed. Now here comes to our experimental results. For image compression, our comparison includes standard image codecs like JPEG, WebP, HEIF, and AVIF. We apply these codecs to holograms extracted from SGD or HoloNet per image, a hologram extraction method, and the learning-based method called DPRC. The rate distortion curves in the above figure reveal two key insights. First, standard image codecs are suited for hologram compression, particularly at low bit rates. These codecs, optimized for perceptual quality in natural images, often discard high-frequency information, which is very critical for holographic reconstruction. And secondly, HoloZip achieves similar reconstruction quality to DPRC, a learning-based method, but at a significantly lower bit rate. This compression efficiency stems from our latent-of-latent strategy, which effectively exploits redundancy in the latent space. For video compression, we conduct experiments on the CVQAD dataset and still do comparison with HoloNet and SGD equipped with video codecs like H.264, VP9, and AV1. From these results, we observe first, although video codecs are able to achieve high compression ratios, applying them directly to compressed extracted holographic videos will lead to a substantial drop in reconstruction quality. And DPRC achieves higher reconstruction quality than these video codecs, but suffers from limited compression efficiency. In contrast, our solution, HoloZip, achieves a significantly better balance, offering much higher compression efficiency while maintaining comparable or superior reconstruction quality. Visually, HoloZip also outperforms baseline methods with less noise and blur, as shown in the zoom-in region. We also do experiments on real optical setup to validate the quality of the produced holograms by HoloZip. Here, we assume since SGD is a per-image optimization-based method, we assume it as the quality upper bound and do comparison with it. As shown in these images, HoloZip achieves very similar visual quality compared to SGD on these tested images, therefore showing our method is able to produce very usable hologram to be deployed on real displays. So in conclusion, HoloZip enables high-quality holographic image and video compression and transmission with vision transformer-based networks. But quantitative results show that HoloZip outperforms existing frameworks for higher efficiency and reconstruction similarity. Qualitative results show superior visual quality from holograms extracted by HoloZip. Yeah, that's all about my presentation. Thank you for your listening.
Yeah, thank you for the nice presentation, Huaizhi. Is there any question from audience? Yeah, if not, I can start. First, like looking at your presentation, I'm wondering like, it seems like you obtain the latent-of-latent space, and then of course we may think one step further, latent-of-latent space, and it can just keep going, right? And then one question that comes to my mind is that how this holographic compression accuracy or whatever metrics that you are thinking of could be like related to these layers of these latent codes that we extract. For example, like if you apply your method for the latent-of-latent or latent-of-latent, like how the results could be different. Like, do you have any thoughts on this one?
Yeah, that's a wonderful question. I think if we further extend to like latent-of-latent, then the quality would, the reconstruction quality would degrade. Like as shown here, compared to like method with like less compression ratio, then our HoloZip actually shows a little bit lower reconstruction quality. But we can achieve a significantly lower bit rate. If we further extend to like triple latent, then I think the reconstruction quality would be further degraded and making it less suitable for displays.
All right, yeah, thank you. Let's thanks again Huaizhi for the nice presentation and answer. Yeah, now we have our last speaker, Dorian. We're going to present the structured light with 1 million light planes per second. Give me seconds.
Hi all, I'm presenting structured light technique that can steer light planes at 1 million times a second. This work is done in collaborations with Professors Praneeth, Yanis, and Aditya. Fast depth acquisition is widely used in industrial quality control, medical imaging, and autonomous driving. To achieve depth, stereo systems are commonly used. They use 2 cameras capturing disparity to get depth. These systems often struggle due to correspondence matching. Actively one of the camera with structured light patterns or by using time of flight information. In this work, we look at structured light scanning, particularly a line scanning technique. Prior art has used DMD projectors, obtaining scan speeds of 240 fps. More faster devices like galvos have also been used, which provide a kiloframe scan speeds. Both of these techniques involve moving parts, and their speeds are limited due to their mechanical inertia. In our method, we propose a system which does not involve moving components, hence no mechanical inertia, thereby achieving 1000x faster scan speeds. Let's see how we achieve that. When light enters water medium, it travels in a straight path. If we place an ultrasound transducer in water as shown in the left and send sinusoidal voltage through it, it vibrates and produces ultrasound in water. This ultrasound changes pressure and in turn refractive index of water, traveling at a speed of 1.5 km per second. Similar to ultrasound, the pressure and refractive index profile are altered in similar fashion as a sinusoid. While we have visualized the pressure and refractive index in 2D, in 3D it looks like this. When parallel light rays enter this pressure field, which we showed earlier, they focus as straight lines and travel forward as shown here. Which means if we have a fast enough camera, we can see these lines moving at 1 million lines a second because we are using a 2 megahertz transducer. But there is no such camera which is as fast as that. So we need to figure out how to slow this down. Okay, what if we turn on the light only when the pressure is at a particular, high pressure is at a particular point? Then we should see a still line. So if we replace the ordinary light source with pulse light source, we should be able to keep this line still, achieving control. And what it means is like if we misynchronize between the pulsing speed and the transducer speed, the misyncronization speed is going to be the speed at which the lines are driven. And in real life, the RGB capture of these focus lines look like this. Here, I'm steering this line at 1 hertz a second, at 1 hertz. To realize the above theory, we created a hardware prototype which consists of a pulse laser, which goes through a convex lens, finally entering water media where a transducer is submerged, which perturbs the refractive index of the water. Together, we call it a acoustic structured light projector. In short, AOSL projector. We direct this to a galvo system which is switched off when the steering is done, when the light steering is done using the ultrasound, and switched on when we are obtaining galvo baselines. And to obtain synchronization between the laser and ultrasound, we use the PLL of the PLL of the signal generator. Using the AOSL projector, we attach an event camera as shown in figure. As event cameras provide sparse asynchronous readouts, which are well suited for structured light, we utilize event cameras. And the focus lines we showed earlier are directed towards the red region here, where the objects are placed to scan. Now that we have our scanner, we first used Galois-based steering to scan two objects, a cat and a dolphin, obtaining their depth. The Galois scans are used as baselines. Then using our method, we first scanned at 10 FPS, 100 FPS, 200 FPS, all the way till 1000 FPS, where we noticed the event camera sensor is bandwidth is limited. These static scenes are only obtained for quantitative comparison. Real interest is in dynamic scenes. For dynamic scenes, we first scanned a motor, which is rotating at 70 RPM. Here, we obtain depth frames at different speeds. We observe motion blur for scans up to 50 FPS, and the results stabilize from 100 FPS and upwards. Then we scanned a fan rotating at 1800 RPM, much faster than the previous case. Clearly, we can observe the motion blur is significantly lower in case of 500 FPS as opposed to 200 FPS. Next, instead of using periodic scenes like fan blades and motor blades, we tested random handheld motions of literals IC and CP. We obtained depth scans at 180 FPS, as shown here. Next, we show the 25 literal suspended with the handheld string and its associated depth scan. With that, we obtain sequential scanning, which means scanning obtaining line scanning when we scan from one direction to other. But we can do much more than that. Our method can place these lines at any location we want in the spatial region. For example, if we wish to scan these two regions marked in green boxes, we only want depth from light plane 1, LP1, and light plane 2, LP2, as shown here. Well, even Galois can do this, but what benefit can we provide? Let's answer this question in detail. At lower speeds, as you can see here, at 30 FPS and 100 FPS, Galois can place these light planes very precisely and without wasting any light. Let's see what wasting light means. As speeds go higher, Galois actually place unwanted light in between these regions, and it smears light. The visual is like a little messed up, but the paper has a proper result where it shows the temporal scan. In contrast, our method can place these planes precisely even at 1 kilo FPS, even as high as like 10 kilo FPS. Do note that our frame rates are slightly adjusted to showcase the line placements precisely. If we obtain the depth from these light placements, we see a behavior something like this. After 150 FPS, we see a serious degradation in Galois scans as opposed to our, which is using an ultrasound. Well, we said we can do 1,000,000 light planes a second, but we only showed till 10 kilo FPS. Event cameras can only do till 10 kilo FPS, so let us see. You are using a transducer which is running at a frequency of 2 megahertz. That means we can place a light plane at a temporal resolution of 0.5 microsecond. By placing two high-speed detectors at light plane 1 and light plane 2, which we showed earlier, instead of using an event camera which has a spatial resolution, we can do a test much better than what we did earlier and test our steering capacity further. So the updated setup looks like this. We have the AOSL projector we showed earlier, and we have a small detector placed in front of the AOSL detector. Whenever a focus light plane passes through this detector, it records a peak. So if there is no peak detected, there is a flat line, and as soon as you see a peak, you see peaks here. Give me 1 second. As you can see, when I'm trying to place a light plane at detector 1 position and a next light plane at detector 2 position, the consecutive light planes are separated by 1 microsecond. When I'm trying to place 100, the next time I try to place 100 light planes at detector 1 and 100 light planes at detector 2, this is the behavior you see. We can also place these light planes non-uniformly, 50 at detector 1, 150 at detector 2, making a 1:3 split. With that, we have presented 1 million light planes a second, because we can clearly see a half microsecond difference between each light planes detected in the case 1. And we also showed how to adaptively scan these scenes. We have some limitations, which is the low laser power makes us use a high aperture lens, causing trouble with the scans because of the depth of field. The line width is a little high, and we can also make it compact using a AOM, but it needs a specialized optical arrangement. With that, we summarize our technique, which provides 1 million light planes a second, reaching the limit of the event camera, placing a light plane at a resolution of microsecond. Thank you.
All right, any question? I have one question. Like here, you are using basically kind of acoustic optics.
Yes.
For creating this really fast moving light planes.
Yes.
I'm wondering, like, what are the actual other patterns that you could generate? Because I still remember, like, in US, we have a really big ocean simulator where they have real mechanical transducer that creates a bunch of different kinds of waves that create specific, like, that could be seen as a kind of structural light pattern. And I'm wondering, like, whether you can do such kinds of stuff by installing the different kinds of like combinations of transducers at different places and create some like more optimal structural light patterns for better 3D reconstruction. Have you
So I would like
thought
to
about
I would like to get a clarification on the question. Like when you say surface, like part of the surface, or do you mean the surface is altered?
Oh, no, I mean just, so my question is like here instead of having one transducer, like
Yes.
is there any way of having it like multiple different transducers in a single water tank so that you can generate more complicated structural light patterns?
Yes.
That could be better for the 3D imaging, those
Yes.
kinds of stuff.
Yes, you can. In the previous iteration of this work, two transducers were used, and we create like dot pattern was used to like do the dot projector, and we realized a line pattern was much better, and we made some changes so that the setup is much more cost effective. Yeah, definitely we can do more than just these two. Yep.
Yeah. Is there any other question? Oh yeah, over there.
So my question has to do with the last experiment you showed, where you have two different photodiodes and you sort of probe them individually, right? If I sort of think about this to generalize it, let's say we have n different sites we want to hit, right? How much does it take to switch between these, and how flexible is the pattern in terms of switching between these sites? And part of the reason I'm asking is you sort of mentioned this number, 0.5 microseconds, coming from 2 megahertz, right? Wouldn't you lose some time sort of transiting the pattern from one state to another? So if you could comment on it, I would love to know some details.
Yeah. So if you remember the galvo scanning I showed, unfortunately the video could not be played properly, but like in the paper we actually show that like the galvo, when it is traversing from point A to point B, it actually floods light through the region, which is basically unwanted region. But we can do 1,000 times faster than that. That means like the light pulse is not getting wasted. So the resolution at which we are able to place these two planes is like at 0.5 microsecond. So not just these two, but we can actually place from light plane 1 to light plane 2 in the region of scan range we have. We can do it at the resolution of 0.5 microsecond. Is that the question you're asking, or like?
Maybe you should take it offline. It kind of sounds complicated. I can talk to you offline. Thank you.
Okay, thank you.
All right, I think then that's it for this session. And thank you everyone attending.